Hello, everyone, and welcome to week 3. Last week we talked about direct proof and proof by contrapositive, and how to use the division algorithm to set those up in a variety of cases. This week we're going to talk about some other proof methods that will help shore up some of our current weaknesses. We're going to talk about proof by cases, and we're going to talk about the principle of mathematical induction, both of which are incredibly helpful in a variety of cases. And finally, I'm going to do sort of an ad hoc collection of other examples of things, where we'll talk about proof by contradiction, we'll do some examples of some classical proofs, and then we'll talk about some other strange things that you're likely to see in higher level math classes that you take after this. But to start with, we're going to talk about proof by cases. And proof by cases is really all about OR. So I want to take this opportunity to talk about what you do when ORs show up in various parts of the hypotheses or the conclusion of a thing you're asked to prove. So first of all, let's talk about what happens if you have something that looks like P or Q implies R. This is exactly where cases comes up. And so what you want to do to start with is you want to say something like, suppose P or Q, and then you want to break into cases. And so you'll write it like this, case 1, P, and then you're going to suppose P, and then you're going to prove the thing assuming that P is true. Okay, and then that will get you through that case. And then you're going to do the second thing, is you're going to do exactly the same thing, but you're going to suppose Q instead, and then you're going to check it in that instance. And so really, what's happening here? If I know that P or Q is true, then I know really there are sort of two universes I might be in. I might be in the universe where P is true, and if I'm in that universe, this proof works. Or I might be in the universe where Q is true, in which case, this proof works. I can't be in the universe where both P and Q are false, because then P or Q wouldn't be true, and so I wouldn't have to worry about it. Now, a common question I'll get, and this is a very good question, is, aren't there really three universes? One where P is true and Q isn't, one where Q is true and P isn't, and one where P and Q are both true. And as long as you're not using something about Q being false in your case, you really only have to check these two. Because this proof works as long as P is true, this proof works as long as Q is true. If P and Q are both true, what have you done? Well, you've really proven the result twice. And proving the result twice is, well, it's not better than proving it once, but it's certainly at least as good as proving it once. So this is the structure that we'll tend to embrace here. And let me do an example of this. So let's prove that if x is even or y is odd, then 3x times 5y plus 1 is even. And here, the OR is super explicit, because I've given you sort of two possibilities. I want you to show that if x is even, this is true, and if y is odd, this is true. So let's start, as usual. So here's where the cases start. So, if x is even, well, what does x is even mean? That means that there exists k and z, such that x is equal to 2k. Note, by the way, when you write case and then thing, you're automatically assuming this is true, so I do not have to now suppose x is even. I've implicitly done that by writing out this case like this, so there is not a need to write an extra sentence here that says, suppose x is even at the start of this. Just, okay, we're now in the universe where x is even. What does that mean? That means there exists a k and z, such that x is equal to 2k. Then 3x times 5y plus 1 is equal to 6k times 5y plus 1, which is equal to 2 times 3k times 5y plus 1. And so if L is that piece, then our 3x times 5y plus 1 is 2L, and so is even. That has finished our proof in this case. But please note we're not done. We've only addressed the possibility that x is even. But it could well be that x is even or y is odd, but x is odd. Because maybe y is odd instead. So that'll be case 2. And so case 2 here is that y is odd. So then that means there exists k in Z such that y is 2k plus 1. So this 3x times 5y plus 1 thing is 3x times 2k plus 1 times 5 plus 1, which is going to be 3x times. So then this will be 10k plus 6. And so if you want, that is 2 times 3x times 5k plus 3. And so if L is 3x times 5k plus 3, then our thing 3x times 5y plus 1 is equal to 2L, and so is even. Which then finishes with this case. And because in all instances of the thing we were proving, either this first part was true or the second part was true, we've now covered all the cases, and so we're done. Again, please note, I did not for this problem do 3 cases. X is even and y is odd, x is odd and y is even, x is even and y is even. I could have done that, but it would have been way messier, and there was no need to in this particular instance. When you're doing cases, you want to signal it very clearly to the reader, and so when you write something like case 1 colon underline or something to this effect to break off a case, that makes it very clear to the reader what is happening. And the thing that needs to be true in order for this to work is that your cases need to cover all the possibilities. It doesn't matter if the cases overlap, as we've discussed, but every possibility has to be hit by at least one case. And then we're done. One more thing that you might notice is that I've used the variable k twice. And the reason why that's okay, whereas normally I would say you can't use the variable k for 2 different things, the reason why that's okay is that this proof in this case takes place in its own little universe. And this universe exists only for the purposes of this case, and as soon as we get to the end of this case, the universe resets, and all of this goes away. So this is like its own little pocket universe. And so by the time we get to here where I've used k again, that k is long forgotten. It's no longer relevant. If you're a computer science-oriented person, you might think about this in terms of scope, where you can use the same variable name in a computer program in a bunch of different places as long as you're careful that those places don't overlap in bad ways, because if they do, then things go badly. The same thing is true here. Of course, it would not be wrong if you wanted to just be safe, use a different letter in the second case, but you don't have to. So we were talking about handling ors, and I told you how to handle an or in a hypothesis. Namely, you use cases. The other thing I want to talk about and make sure we know is how to handle an or in a conclusion. By the way, those are the parentheses I meant for you to read these with. How do you handle an or in a conclusion? Well, we've talked about one way to handle an or in a conclusion, and that way is by far the most common. Here is where I would make you all shout out the answer of what you're supposed to do if there's an or in the conclusion, but unfortunately, life being what it is, I will just have to pretend you all shouted out contrapositive. But to reiterate, because this is important, an or in the conclusion is usually an indication that you should be using proof by contrapositive. And the reason why this is helpful is that the contrapositive of P implies Q or R is not Q and not R, implies not p. And so taking the contrapositive lets us transform something with an annoying or in the conclusion to something with a very helpful and in the hypothesis. And remember, ands in the hypothesis are great. They're the opposite of ors, in a sense. Instead of having to split into two universes, where thing 1 is true or thing 2 is true, I get to be in the best of both worlds. I get to be in a universe where two different things are true. So that's great. Sometimes, though, this is not actually helpful. Sometimes taking the contrapositive of the statement we want to prove doesn't actually yield good results. And so in those instances, we have to resort to other tactics. Here is one such example. So here we're asked, prove that if I start with an integer, then x squared is a multiple of 4, or x squared is 1 more than a multiple of 4. So how are we going to handle this or? Given that I think you'll find if you attempt to take the contrapositive of this and prove that, it does not go super well. And here's where we need to use a second trick, or a backup trick, if you will. Which is that P or Q, as we've proven before, is logically equivalent to not P implies Q. So what I'm doing here is I'm going to rewrite the or as an implication. And so then the thing we're trying to prove becomes that if x is an integer, and x squared is not a multiple of 4, then x squared is 1 more than a multiple of 4. In other words, just if not the first part, then the second part. So we'll go ahead and suppose that x is an integer, and x squared is not a multiple of 4. Now, I claim this implies that x is odd. This is a structure you'll see a lot in proofs, particularly as proofs get a little bit more complicated, which is that you'll see someone write a claim in the middle of their proof. And what they're saying is, I'm saying this thing is true, but I want you to read the thing I'm saying is true before I explain to you why it's true. So this is, again, someone showing you, okay, what's going to happen with this proof is I'm going to convince you that this means x is odd, and then from there I'm going to go on to show you the rest of this thing that I want to do. But then you get a little proof inside the proof to see that the claim is true. And so what you'll often see people write is something like proof of claim. And we actually prove here the contrapositive. And the contrapositive here is if x is even, then x squared is a multiple of 4. So to prove that, we'll suppose x is even. So there is some integer k, such that x is equal to 2k. And then x squared is 2k squared, which is 4k squared. And so if m is k squared, then x squared is 4m. And so x squared is a multiple of 4. That finishes our proof of the claim. So here we really have done a proof inside the proof to get this. But again, once the reader believes this part that I've written in red, they can now just ignore it forever and just think about the blue piece and the black piece. Again, what you're really doing when you're writing something like this claim structure inside a proof is that you're really compartmentalizing the different pieces of the proof so that the reader only has to think about a small piece of it at a time rather than having to think about the whole structure. So now we get to resume back where we were before we wrote down the claim, which is that we supposed x is an integer and x squared is not a multiple of 4. By the claim, that now tells me that x is odd. Now, again, please note, the claim thing only worked because we proved it. Claiming things is not a superpower. You cannot just write claim and then just go on pretending that it worked, although history tells me people will try that. But you really have to prove the claim before you can use the claim. But we have proved the claim, so we can use it. So since x squared is not a multiple of 4, x is odd. And so there exists k in z such that x equals 2k plus 1. So we follow our noses. X squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1. And so if m is k squared plus k, then x squared is 4m plus 1. And so x is 1 more than a multiple of 4. And so that now completes our mega proof. The more steps go into your proof, the more structure starts to really matter, and the more it becomes really important that you're clearly communicating to the reader exactly what is happening as they're reading this. I want to point out an alternate structure here, which is one you'll often see in textbooks, but not one I anticipate that you'll use yourself a lot in your homeworks. But the alternate structure is to write what's called a lemma. And so the lemma would be something like the claim that we did in the previous example. And so it would be something like this. If x squared is not a multiple of 4, then x is odd. And so the strategy you'll often see books employ is that they'll write down a lemma, usually out of nowhere. They'll prove it, and you'll be like, great, this is now a true thing. And then they'll write down the actual interesting thing. And then in the proof of this proposition, it will say, well, by the lemma, blah, 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 blah. So just to contrast, when you see something written like this, what's been done is, rather than introducing the claim in the middle of the proof and proving it in the middle of the proof, they have pre-anticipated that they're going to need this claim, and so they've pulled it completely out of the proof and done it first. Note you'll also sometimes see textbooks do it the other way. They'll state the proposition, they'll prove the proposition, and then they'll say, the proof will be done once we've proven the following lemma, and they'll actually put the proof of the lemma afterwards. So, what is someone saying when they call something a lemma? When someone calls something a lemma, what they're really saying is, this is something which I'm proving only because it is a stepping stone to a larger result. And so, if someone calls something a proposition or a theorem, they're usually implying that it is interesting in its own right in some way. Whereas if someone calls something a lemma, usually they're saying somewhat disparagingly, okay, well, this result isn't very interesting, but hold on, it's going to be worth it when we put it to use in the next bit. So, in terms of the truth value, a lemma is no different than a theorem or a proposition. It's just a thing that's true that we've proven. But when someone calls something a lemma, they're really saying, okay, this is sort of the halfway point between where we are now and the thing we want to prove. And so if you look at these gigantic 50-plus page proofs, usually the way they're actually structured is that there'll be a lot of little lemmas along the way, so that you only have to think about one piece of the proof at a time, rather than thinking about the whole thing. So, that was a rather long-winded discussion of proving that if x is an integer and you square it, then you get something that's either a multiple of 4 or 1 more than a multiple of 4. Which is pretty evocative of our buckets from the division algorithm, right? Multiple of 4 was 4k, 1 more than a multiple of 4 was 4k plus 1, and then there was the 4k plus 2 bucket, and the 4k plus 3 bucket. And what we just said is the squares of integers only ever fall in these two buckets. They never fall in these two buckets. And that's kind of surprising. And our proof of that actually ended up being a little bit involved. So much so we had to define new words and proof techniques to do it. But there's actually a different way to go about this. And I want to show you this other way to do this, which is to fall back on what I talked about before, which is to use cases. And I'm going to call this making your own cases. And really, this section on proof by cases isn't so much about proving statements where it is given to you as an or. We've done those before by basically arguing through this without using the word cases, or in at least one case, even just using the word cases. The real meat of this section on proof by cases is actually proving statements where there's not an or written in the hypothesis, and you make your own or in the hypothesis. And let me show you what I mean by that. So now what I'm going to do is I'm going to reprove the result that we proved before, but in a way that I think you'll find a little bit more amenable. But in order to do that, we're going to have to invent our own cases. And what I mean by that is that I'm going to observe that for every integer, I know that integer is either even or odd. Now, at no point in the problem does it mention even or odd. So really, you have to understand what's going on in order to think that, hey, maybe actually what I want is to think about evenness or oddness in order to get some result like this. So, in other words, these types of questions, the ones where you have to make your own cases, are going to require some level of creativity, some level of understanding what's really happening underneath the surface so that you can make this work. But now, here's the point. I have made my own OR statement. And so this OR statement lets me break into cases. So my first case here is that x is even. What does even mean? Well, it means that there exists an L such that x is 2L. I'm not, by the way, using k here because I want to use a k in my punchline. And so I'm just pre-using a different letter so that I have the letter k free so that I can match the statement that I was given. So once we've thought to do this step of then x is even or x is odd, everything else pretty much falls into place on its own. I can just follow my nose through this like you usually would. Okay, so if x is even, then what happens? Well, then x squared is this, which is that, and letting this equal that, we get this. And, well, what's the other case? Well, maybe x is odd. And so if x is odd, then x is 2l plus 1, x squared works out to be 4l squared plus 4l plus 1, and so if k is l squared plus l, then x squared is 4k plus 1. Now, thinking of even and odd might require a bit more creativity, maybe a bit more faith, but you might also think, okay, well, this whole question is really about the mod 4 buckets. And so it might also occur to you, as you think about this question, that, hey, maybe what I really want to know is which of these 4 buckets x lives in. That is x in the 4k bucket, the 4k plus 1 bucket, the 4k plus 2 bucket, or the 4k plus 3 bucket? And in fact, that works too. You can, in fact, instead of breaking into 2 cases, like even and odd, you can break into 4 cases, which would be these, and then everything also works out. So certainly there are lots and lots of different ways to prove the same thing, and you only have to find one of them, and once you've found one of them, you know the thing is true. I want to follow up on that previous example just to give us another opportunity to do cases in a very similar context. I think this would be an excellent example, by the way, for you to pause the video, try and work out, and then after you've done that, watch me do it. So now what we're going to do is we're going to suppose that x and y are integers, and then by our previous work, there exist m and n and z such that x squared is 4m or 4m plus 1, and y squared is 4n or 4n plus 1. All I've done here is to apply this result that we just proved, but I didn't use k because there's a k in the result I'm trying to prove, so I saved that letter for later. And so I used m and n, but I can apply this result equally well to x squared and y squared, so I did both. So now, because of these ORs, I can break into cases. How many cases? Well, as it happens, there's going to be 4 cases, based on which half of this OR I choose and which half of this OR I choose. And this is not too uncommon that you'll have cases that really stem from making two choices at once. So here's our first case. The upside of the fact that we have 4 cases is that the 4 cases are all very short. Because in this case, for example, x squared plus y squared equals 4m plus 4n equals 4 times m plus n. And so if k is m plus n, then x squared plus y squared is 4k. And that appears just instantly, because it's almost exactly the same as this. And so I get to do that. And I get to do this 2 more times. Now, what we were asked to show was that x squared plus y squared is 4k, 4k plus 1, or 4k plus 2. And if you look at our cases, in case 1 it was 4k, in case 2 it was 4k plus 1, in case 3 it was 4k plus 1, and in case 4 it was 4k plus 2. And so in all the cases, the thing we're asked to prove is true, and so we're done. Now, I've mentioned before that a lot of proofs are short but difficult, and a lot of proofs are long but easy. I think this would fall under the long but easy category. Basically, as soon as someone writes this first line, the rest of the proof basically writes itself. There's just a lot of it. But we end up here. Now, for reasons you might be able to imagine by the end of this first of multiple videos about proof by cases has a bit of a bad reputation, because they tend to go on a bit, and they tend to be a little bit tedious relative to a lot of the other proof methods. Further, I want to note that in terms of making sure all of your variables and notation line up, it can be a bit of a nightmare. In fact, I have had to reshoot parts of this video more than any other video because I kept accidentally choosing letters that overlapped. And so don't worry if you do the same thing. You're going to make mistakes, and that's why ultimately you type these proofs so that you can pretty easily edit them and fix the various errors that come up as you work through them. All right, allow me one more tiny bit to say about this particular example and what we've just proven, and then we can wrap up for today's video. So, by the division algorithm, there are 4 kinds of numbers. Those that are 4k, 4k plus 1, 4k plus 2, 4k plus 3. The first thing we proved was that squares all land in these first 2 buckets. That is, if you square any integer, you always end up in this half, never in those 2 buckets. The next thing we proved was that if you sum 2 squares, you always end up in one of the first 3 buckets. And so in particular, one way to frame what we just proved is that a sum of 2 squares is never 3 more than a multiple of 4. Fermat and many others have been very interested in the question of which integers you can write as a sum of 2 squares. So here is a giant table that shows you my work of which numbers can be written as a sum of 2 squares up to 36. Here, if the number can be written as a sum of 2 squares, I've shown you one way to do it. So for example, 17 is 1 squared plus 4 squared. And if a number cannot be written as a sum of 2 squares, I have just written an x. So for example, it will not take you very long to check that you cannot find 2 squares that add to 6. Now, this is a fairly complicated pattern. And you'll notice the way I've written this, there are x's sort of all over the place. But one observation that probably stands out to you more than any other from the way I've written this is that there is this giant pile of x's in this column. And this giant pile of x's in this column is basically the sum total of all of our work from today. Because this is the 4k plus 3 column. These are all numbers that are 3 more than a multiple of 4. And what we showed, putting together basically everything we did today, is that if you sum 2 squares, then you get something that is in one of the other 3 buckets, but never this bucket. And so no matter how far you continue this pattern, you'll always have x's in this column. Now, of course, we didn't really say anything about why there are or aren't x's in other places. And that, I guess I'll have to leave as a mystery for you to think about and see if you can think about what the pattern is here as far as where the other x's are. But at least as far as this column, if you understand everything we've done today, this shouldn't be a mystery. We know why all of these x's are here. Alright, in the next video, I will do more rapid-fire examples of proof by cases for you, so I'll give you several more of those. And then after that, we'll proceed onward to talk about proof by induction. But that's all for now. Hopefully you enjoyed this. I'll see you next time.